And we have one student who is going to do asynchronous. All right, so now let's say we are given a table with the following columns: name, social security number. No, not this one, sorry. We're given customer ID, account number, balance, last transaction, customer name, and an email. So first thing we want to do is when we use, so first of all, the first number phone should be okay because there's no column with multi-values, right? So this table should also has a primary key. So then this first number phone should be satisfied. Now we just need to work on the second number phone, okay? Second number phone basically says that where there's no partial functional dependencies, right? So first of all, we need to decide what is the primary key for this table. So we have customers information or account information. So just use your common sense, use your knowledge of one-to-many, many-to-many relationships. So one customer may have multiple accounts, one account may have multiple customers. Let me double check, okay? So is it possible that one customer have multiple accounts? Let's see, one customer. So for example, 9087, there's no, and then 2098. 2098, yes. So this customer has multiple accounts. And then account number, does one account have multiple customers? Let's check. So this, yeah, we do have one situation like that. This one, or one, yeah, 375 account belong to 3 different customers. So therefore, this is really like a many-to-many relationship between customers and account. So therefore, the primary key should be like a both, right? Should consist of both customer ID and account number. So let's just work on that. So we're going to create a new whiteboard here. Okay, so primary key will be equal to both customer ID, comma, and account number. 2 columns, okay? And then that's the first step. So this has a primary key. Second step, we need to draw functional dependency diagrams. So let's just do it on here. So let's see, we have customer ID, an account number, and then balance, and then last transaction, and then customer name, finally email. So we already decided that this is a primary key. Okay, customer ID and account number join to form a joint primary key, composite primary key. So then we draw functional dependencies. So apparently, customer account number determines the balance, right? It does not matter how many customers in the account, but there's only one balance, right? And then customer ID should uniquely determine the last transaction and also email, right? And then what about last transaction? I think last transaction really depends on both, I believe. Can you tell that? So for example, let's just use this account, okay, 375. This is 375 have this last transaction. 375 have this last transaction. So different customers have different last transaction. You see that? Right. So 375, you see that they have 3 different transactions. So have 3 different transaction days, 1 for each customer. So therefore, that is a column that depends on both. So I'm going to draw functional dependency between the last transaction and the whole primary key. So this is FDD. based on this FDD, we know that there is a partial functional dependency because the balance depends on the account only, customer name and email depends on the customer ID only. They are not whole primary key. They're only part of primary key. Whole primary key has to have 2 columns, right? So the table is not in second normal form. Of course, if it's not a second normal form, then it should not be in third normal form. Okay, so you have to always start from the first normal form and then second normal form and then third normal form, step by step. Okay. So just give a reason because of partial functional dependency as account number determines balance. Okay, and also customer ID determines customer name and email. So as long as you have one such functional partial functional dependency, that they have a dependency that something depends on only part of primary key, then you you have enough evidence to make a judgment to say that's in violation. You don't have to have 2, okay? But in this case, we have 2, so we need to we have more than enough evidence to say that it's not in second normal form. Now after that, we are ready to fix it. So what we do is we write every part of the primary key line by line. So let's say account number and the customer ID, and then account number, and along with customer ID together, both together, okay? And then we need to write every line, every part of a primary key one by line, and then we put those columns that depends on those part of primary key after each part of primary key. So say we say balance depends on account number only, and then customer name and the email depends on customer ID only. And also in this case, we have one column, which is last transaction, depends on both. Okay, so that's the second step in the procedure. The third step is to create a table. Okay, so basically we have 3 tables created. For each line, we create 1 table. So the first table is account number and the balance. With account number as a primary key. So the determinant, the left-hand side, the determinant is going to be the primary key. Okay. Marina, your password for attendance is review.
Okay, thank you.
Yeah, we are reviewing your homework question number 1. Now let's say for the second line, we create a table for customers. So there's customer ID, which is the primary key, and then we have customer name and email. That will be your second table. And then we have one more table that here's account number and the customer ID as the primary key, join the primary key. Account number and the customer ID jointly. And then this one has one column, which is last transaction. There we go. So we end up with 3 subtables, and which will be in second normal form because second normal form procedure is clean, right? So if you wonder what's the relationship between the 3 tables, so you have a table about accounts, and you have a table about customers, and this is really like they're joined. They're joined table. This is like a gerund, right? So if you want to draw like ER diagrams, then you're going to have something like this. You're going to have account. You're going to have customers. Okay. And then you're going to have a gerund in the middle, which is showing the transaction, last transaction. So let's just say you have let me just do it bigger. Do something bigger than that. So I'm going to put in here. So that would be transaction. So you have an attribute called last transaction. Transac. Okay, last transaction. And then you have customer. So then this is gerund. So you're going to have relationship like that, relationship like that. So by doing that, this account number, which is ID here, and the balance, which is describing attribute. Okay, and then for customer, you have customer ID, customer ID, I think. And a customer name. And then what is the email? Okay, so let's just put this attributes here. So then this is a gerund in the associative entities. You're going to put customer ID into there and also account number into there, not only as foreign attributes, but also as part of a primary key. So therefore, you have this junction. This is more like a gerund. The table for the gerund has two foreign keys, and then they also form a joint primary key for the gerund. Okay, so that will be if you follow ER diagram, the business modeling approach, then you're going to design these three tables instead of this original one table, like this one. Okay, this table will have actual redundancy according to second normal form criteria. Okay, now we need to check to see whether this table is going to be in a third normal form. So we check these three tables. And this table, I would say, is automatically third normal form because it has only one non-key column, right? Do you remember the shortcut? The shortcut approach. So if a table has only one non-key column, then third normal form is automatically satisfied. Of course, you have to make sure it's second normal form to begin with, because we already said this is a second normal form, and that this table has only one non-key column. So this table is already third normal form. Now, what about this table? Second table has only one primary key column, so then that's second normal form, all right? And then it has two non-key columns. So now we just need to decide whether there is any functional dependency between customer name and email. So in other words, will email determine customer name or customer name determine email? What do you think? Will customer name determine email? Of course not, right? But will email determine customer name? Possibly, yes. So email, assuming everybody has unique email, so there's a possibility that you have this functional dependency. Email determines functional name, right? And then so this table, if that's the case, then this table not in third normal form. Now, what about the last table? Last table has only one non-key column, so that is automatic third normal form, because you cannot find a second non-key column that depends on this last transaction or determined by this last transaction. So this is already in third normal form. Okay, so now let's say how can we fix this the second table. To do that, I'm going to use this transistor to make a new table. So that will be email, okay, and then customer name. Okay. So that's based on that the functional dependency, which is email transistor determines customer name. Okay, so based on that functional dependency, we create this table. All right, and then everything else from the original table, original table, everything else just customer ID, right? Because they take these columns, these two columns off, then only customer ID left. Everything else, so that will be customer ID only. Okay, plus transistor. So you need to put a transistor, this email back to here as a foreign key, right? So basically just like that, right? You have to make just put that transistor back to the second table along with everything else. So everything else that was original primary key will be still primary key. So now you have two tables. Okay, two tables broken up tables from broken up from this table. So now this is this table is not in full normal form, but now it's fixed. Okay, so now they both should be in full normal form now because each has only one non-key column. And there we go. Now, is this a good design? It's questionable. Because if you use this one, basically you have to assume that email address is going to be some kind of a key for this table, okay? Some kind of key for this table. So this is questionable design, but according to this normal form, that's how you get it. According to this normal form, okay, if you're assuming that function email address can uniquely determine customer name, then yeah, that's the only result, okay? So there's always like a trade-off. So is it better to are these two tables better than original one table? Is it better than one original table like this table? This one is it better than this one? Not necessarily. So it's kind of a it's always it's a trade-off. So between small tables and large tables, we talk about that last class, right? So this is actually you can argue either way. Okay, so I'm going to leave that as like a open question for you to think. So in what situations this table is better than the second one, than these two tables, and in what situations this is better than the one original table, like table this one. So without breaking this up, okay, is better than the other two. Okay, so it probably depends on different scenario. What scenario you're going to use these tables. Okay. All right, so then basically based on the procedure, then that's how we do it. But now let's do the second question. Second question is a little bit more involved. Let me look at the questions first, because it has like a repeating columns, repeating values. So here we have order ID, order date, customer ID, customer name. So if you look at the values, they're all single valued, right? Each one has only single value, each cell. But then when you come to the address is also single value, even though it has multiple lines, but it's a single value, right? It's just straight address. But then when you come to the item ID, item name, each order has a multiple item ID. See that? And also multiple item names, a multiple unit price, multiple quantities, and also multiple subtotals. Okay? And then each one has one order total. That makes sense, right? So basically each order is going to have a multiple items. These are the items, right? Each item has like a subtotal, and then has one grand total. Okay? So we have this 1, 2, 3, 4, 5 columns, which are multi-valued attributes. So therefore, this table is not in first normal form to begin with. So we need to fix that. Okay. So now let's see how can we fix. Okay. So let me do that. So first of all, I'm going to take those multi-valued attributes out into a separate table, along with the primary key from the original table. So what is the original table primary keys? Of course, it's order, right? Order ID. So you're going to use order ID along with order ID and then item ID together to make a key for this line items. So you're going to create a table with subtable, which consists of item ID Let me just move this, make the answers available here. Item ID, item name, and then unit price into weak entity table, and quantity, and then subtotal. So that will be weak entity table. Besides that, we need to copy the original primary key from the original table along with this weak entity. Remember, weak entity you have to get a primary key from the strong entity. Strong entity in this case would be autos, right? So you need to get an auto ID as a foreign key and also as a part of a primary key. So what will be the primary key for this weak entity is going to have a auto ID and also item ID, I believe. Right? So if you know the auto and also the node item ID together, then you should be able to uniquely identify each line item here, right? Does that make sense? So this 1015 for this auto is not going to be same as any other line items. And there's a 1025, and this one also have 1025. However, they have different orders, so therefore they are not the same line items. So after we have the primary key duplicated as a foreign key, and then use that as part of a primary key for that, and this is, so we can name that table. This table is about really. Let's just name the tables later. Just for now, we just follow the weak entity design, and then we move all the attributes, move all multi-valued attributes out, and then we create a weak entity table for that. And then everything else will be remaining in the original table. So let's just do. So everything else in this case will be. Let me just expose this also here. So will be auto ID. That will be primary key, of course. And then you have auto date. And then you have customer ID. And then you have customer name, customer address. That's it. And then auto total, which is last column. Okay. Now, you did not ask a question. I think some people may think that we ask that the customer whether customer ID should be also part of the primary key. I don't think so, because yes, one customer may have multiple orders, but each order has only one customer. Okay, you see that? Each order, this order is for this customer, and this order is for this customer, and this order is for this customer. Okay, but one customer may have multiple orders, but each order is going to have for one customer. Does it make sense? How can you tell? Well, you don't say that order ID is duplicating, right? Do you say order ID is duplicating in this column? Okay, also based on our common sense, each order is only for one customer, right? So you're not going to have like a shared order, right? So therefore, order ID should be primary key, should not need a customer ID as a part of a primary key for this problem. Okay. All right. So after that, we fix the first normal form violations. So now you basically just say each item, each order ID will have like each line item. So basically, you're going to have each of this line will come here as one record, come here as one record here for this table. Okay. So after we fix the first normal form, then we need to consider second normal form. Okay. So let's consider second normal form. To do that, we need to understand what's the primary key and what is functional dependencies also. Okay. So first table, let's just take a look at the first table. Okay. First table has two key columns. So therefore, there's a possibility of of second normal form violations. Okay, so there may be partial functional dependencies. So let's take a look. What are functional? So first of all, primary key for let me say the primary key for this table is it will be order ID and item ID. So 2 columns, okay? And the primary key for the second table is just 1 column. So it will be just order ID. Okay, you can stop with me, ask questions, okay? Just assuming that you understand everything, but if not, then just stop with me. So we decided the primary key, and then now let's draw functional dependencies. So first of all, we can see that there's item name, item ID should determine item name. Item ID should functionally determine item name, and also should determine item unit price, unique price, right? And the quantity and subtotal, of course, will depend on both. So in this case, we have order ID and an item ID determines the quantity and also subtotal. So these 2 columns depends on the whole primary key, but these 2 columns, item name and a unit price, is depends on item ID only. So it is a partial functional dependency, right? So therefore, the first table violating second normal form. Okay, so let's see how we write that. So let's just say this table is not in second normal form due to partial functional dependency, which is item ID determines item name and the unit price. So as long as we have 1, that's enough to make judgment of second normal form violations. Okay, so now let's see how can we fix that. To fix, we are going to list every part of non-key, every part of a primary key line by line. So order ID and item ID. So line by line, order ID and item ID, and then together order ID, comma, item ID. And then let's say what depends on which. So there's nothing depends on order number only, order ID only. So just nothing there, okay? And then item ID will determine item name. We already said that. And also unit price. You see that? And then what determines what does order ID and what do either order ID and item ID determine? They determine other 2 columns. So they are quantity and the subtotals. Quantity and the subtotal. So because of that, we end up with 3 tables. The first table just have 1 column order ID. Second table has item ID and item name, and then unit price. Item ID is the primary key. And the third table is put here. We have 2 key columns, order ID and item ID. These 2 columns has 1 primary key, and then quantity and the subtotal. Yeah. Okay, so you see the first table is broken up into 3 tables. So you may have a question: do we really need this table? Order ID, just one column table? Yes, you do. You do need that because this representing that original information has like order ID information or just one column which has all IDs. Okay, so you have to follow the procedure. There is a possibility that this table may be merged with another table. Maybe other table has more information about orders, but for now there's none. Okay, so for now we can just leave it here. Okay, so now this is the first table out of the weak entity is broken down into 3 subtables. Okay, and then so they will be in the second normal form. But now let's look at third normal form to see whether this the resulting table is in third normal form. So let's take a look. So this table has no problem because it has no non-key column. So that this table should be automatically third normal form. Okay, and what about this table? This table has 2 non-key columns. So we need to say whether or not one of these non-key columns determines the other. Where item name determines unit price, or unit price determines item name, probably neither, right? Item name, maybe many items have many products have the same name, but they have different price. They are different items, so therefore they have different price. And the price cannot determine name, okay? So this table should be fine with third normal form. And what about this table? Last table, quantity and subtotal. Will quantity determine subtotal? Not really. Quantity, really, if you have a price, then you can determine subtotal, but you cannot. Okay, with quantity alone, you cannot determine subtotal. Subtotal cannot determine quantity either. So therefore, this table is also in third normal form. Okay, so it's good after second normal form breaking down. The first table is already in the third normal form. So now we need to check the second normal, the second table. The second table is already in second normal form. Why? Because it has only one primary key column. Okay, so in that case, part is whole, whole is part. So there's no partial functional dependency. All right, and then we just need to check third normal form violations. So do we see any? So after that, we have primary key determinant, right? So let's draw functional dependencies here. I believe there are something there. So for example, customer ID should determine customer name, and it should also determine customer address. Is that right? So customer name, customer ID is non-key column, customer name is non-key, this is non-key. So therefore, we have functional dependency that it has that is just like one non-key column depends on other non-key columns. So therefore, this table violates third normal form. So this is not in third normal form. So now let me say if I had let me see what I would do. So let me just see whether I can copy this. Can I copy this? Or if not, I can just draw a line here. So let's draw a line all the way down. All the way down. It's not a good, okay, draw all the way to here. Okay, so the table is not in third normal form because of transitive functional dependency, which is what? Auto ID determines customer ID, which determines customer name. And the customer address, right? So this is a transitive functional dependency. We have non-key column determines other non-key columns, okay? And now, after that, we're going to see how do we fix. So to fix, okay, we use the transistor and its dependence to make a new table. So customer ID determines customer name and the customer address. And use that to create a new table. Customer ID and the customer name and the customer address as columns. And the determinant is this determinant or transistor is going to be primary key for the table. Okay, so this is the first table. Second table so is going to use everything else except these 3 columns. Okay, everything else except these 3 columns to make a new table. So what is everything else? Let's look at that table again. So everything else we include order ID, order date, and order total. That's everything else. Okay. So everything else will be order ID, order date, plus order total. So those are everything else. But then you have to add a transistor back, so the customer ID will have to come here again. Customer ID. So this is essentially like a foreign key coming from here, right? Okay, so everything else plus the transistor make a new table. Then original primary key will be still primary key for the new table. Get that? So therefore, the second table is broken down into two tables, one for customers and one for orders here. Okay, and then you say the relationship between this is just a customer and order. One customer may have many orders, right? Have many orders, so therefore it's one-to-many relationship in here. Okay. Now the third normal form may not be clean. The fixing may not be clean, so we need to check again to make sure that each subtable is still in third normal form. So for this first table, we check the customer name and the customer address. Do they depend on each other? Probably not. So this table is already third normal form. And now what about this table? The second table. Second table has 3 non-key columns. So we need to check, say, where's the order date, order total, and the customer ID have some kind of functional dependencies. I think probably not. Probably not. There's no functional dependency between order ID, order total. They don't have relationship, right? Order date and the customer, no relationship. Order total and the customer ID, no relationship, right? So therefore, you can just simply say this is already in third normal form. Okay, so after breaking down the two table, original one table, fixing the first normal form violation, second normal form violation, and third normal form violation. So we end up with how many tables? We end up with one table here, two tables here, and then originally we also have 3 more tables here. We have this table 3 and table 4 here. And then what about this table? Now, if you look at this order ID table, order table just has order ID, which is really subtable of this one, right? Subtable of this one. This table is going to have all IDs, and also besides that, it's going to have order date, order total. So therefore, this table is not really. So this table can be removed because this table is part of another table. So essentially, we end up with 4 tables. Okay, so now let's look at the relationship among the 4 tables. So first, we say customer and order, the relationship, and then we have a table about items here. Okay, and then what about this? This is really gerund. You see that it's gerund between item and order. So essentially, you're going to have ER diagrams like this. So you're going to have customer who have many orders, and then items, and then there's a gerund in the middle, which shows quantity and sub total, and that's gerund, which was really the originally was a many-to-many relationship between order and items, right? But now besides that, we put like a quantity and subtotal as data for this relationship. So we create an associative entity in here. So for customer, you have attribute like customer ID, customer name, and and the customer address. For orders, you're going to have order ID, order date, and order total. And for items, what information you have for items? For items, you have item, this one. For item ID, item name, and the unit price. Okay, and then the gerund has these 2 attributes, and these 2 will be just like the primary key duplicated inside gerund as a foreign key, and also as a part of primary key. So you put order ID into here and item ID into here as foreign key, and also as part of primary keys, part of primary key. Yeah. So basically, the gerund is going to have two key columns. Okay. And 2 foreign keys, and 1 primary key consists of order ID and item ID. All right, so that's just for this answer to your homework question. Okay, and then for today's class, I still have one more normal form to finish, and then after that we'll do review. Okay, so we basically this is just like a review of your homework. So now let me do. Anybody has questions? Does anybody have questions about this answer?
So, Professor, we have few missing values in the table. So, how do we have to handle that?
Say, ask a question again. What is it? I feel what?
In the second question, there are some missing values.
Second question, you have what? Okay, the second question.
Yeah, there are some missing values like for
Okay,
order.
missing values. Okay, missing values. Missing values is the missing values just basically saying those attributes can be optional, so you cannot do anything. You cannot do anything. They are fine.
Okay.
Yeah. So remember that for first normal form basically says that you cannot have duplicating values. Okay. No normal form says you cannot have missing values. Some columns may have missing values, but if you have like structural missing values, then there will be a problem. But in this case, we're just assuming that you may have auto that the customer missing the customer name and address. Okay, the item may also missing item name, item unit price. That just maybe just like a database saying that this column can have missing values. This column can have missing values. They are fine. They are not a problem for fixing this first normal form, second normal forms. Okay.
Okay. So, while solving the problem, we do not have to include the data in tables. We just have to draw the structure.
No, you don't have to include any data. Just make sure that you understand the data is included just as a sample to tell you that there might be some kind of functional dependency that may not be able to easily see. So you can the data make judgment. Okay.
Yeah. Okay. Thank you.
Yeah. Anybody else has questions? If not, I'm going to open up the PowerPoint, see which part we did not finish last time. Okay, so this is the original PowerPoint. Let me see. So we did that. Second normal form, we finish it. For normal form, we finish it. Then for normal form, we did that too, right? Title, second normal form violation fixing. And I think we did that. Second and fourth together, just remember that, just say every non-key column depends on the entire primary key and nothing else, okay? So I'm going to go to next normal form called a Boyce-Codd normal form. And this normal form is very beautifully stated. So I like this normal form more than any other normal forms. So let me go to show the screen, show the slide show here. Okay. So a relation is a table, is in a Boyce-Codd normal form. Okay, if every determinant in the relation is a key. Okay, so remember, note that there's no need for any other normal forms as a precedent condition. For example, like a second normal form depends on the first normal form, and a third normal form depends on the second normal form. But this Boyce-Codd normal form does not say anything like that. Okay, does not depend on any other normal forms to begin with. Secondly, it does not need you to identify PKs. Okay, so only thing you need is draw all possible functional dependencies. If you found one functional dependency that the determinant is not a key, then it has violation of Boyce-Codd normal form. Okay, So to do that, to check Boyce-Codd normal form violations, first of all, just draw functional dependency diagram. Okay, and then check if there's determinant for every functional dependency. For every line, you draw functional dependency diagram on a functional dependency diagram. You ask if the determinant is the key for the table. If it's not, then it is a violation. If yes, then you can forget and then move on to next functional dependency, check again. So if you found any functional dependency that has a determinant which is not a key, then you have a violation. Okay, does it make sense? So let's just look at this table, sample table here. So branch name, customer name, loan number, account. Okay. So if I'm going to ask you for second normal form violation or third normal form violations, then we'll have to ask you what is the primary key for the table. But for this Boyce-Codd normal form, I don't have to ask. Okay. I just draw functional dependency diagram to see whether there's any functional dependency that pop up that can get us attention. Okay, so I have one here. So of course, no matter how the relationship between branch, customers, and loans, there may be different kind of relationships. However, loan number always determines loan amount, right? Does it make sense? Loan number should always determine loan amount. Okay, so therefore we have a functional dependency. The determinant is loan number. Now you ask, is loan number the primary key, or is loan number a key for the table? In other words, will loan number determines customer name and also branch name? Possibly not. You know that there are possibilities that maybe several customers jointly apply for loan. So one loan may belong to several customers. Make sense? So therefore, the loan number definitely will not determine customer name. Okay? So therefore, this table is violating third normal form. Is violating Boyce-Codd normal form, because we have functional dependency. The determinant is not a key. Okay? So in this so let's just say how we write down the conclusion, how do we write our judgment. Okay, so loan number is determinant, but loan number is not a candidate key for the table because a branch has many loans. A loan may belong to several customers jointly. Okay, so therefore the table is not Boyce-Codd normal form. So you have to justify that the loan number cannot determine every other columns. Okay. Okay. Now how do you fix Boyce-Codd normal form? Well, we said that basically just need to do the same thing as third normal form violations. So it's just in the same procedure you fix third normal form violation as for Boyce-Codd normal form. So first of all, for the functional dependency that are non-key, you have like a determinant which is not a key. You use that functional dependency to make a new table. So in this case, we have loan number determines amount, right? So make a new table with loan number as a primary key for table. And then everything else from the original table. So remember, original table have branch name, customer name, loan number, and amount. Now you remove these two columns. So everything else will be just a branch name and a customer name only, right? All right. So then plus the transistor. So you still need this. Use this. Put this back. Put this. This transistor back. So this the determinant which is not a key. Okay. So you make that table. Add that back to the remaining columns to make a new table. So originally we have branch name, customer name, right? Everything else plus the transistor. Okay, to make a new table. So the result will be just two tables like that. So regarding what is really, what is the primary key for this table? There are two possibilities. So first of all, customer name and loan number, definitely they don't depend on each other. All right. So one customer may have multiple loans, and one loan may have multiple customers. All right. But what about branch? So this is situation here. Maybe there's a branch. The branch can issue a loan number independently. Maybe. So in that case, a branch, say for example, loan number 112, and one branch have 112, another branch also can have 112. So in that case, loan number will not uniquely determine the branch. Okay, and there's a second possibility that the loan number is unique for the entire corporation. Each branch basically just use whatever loan number is issued by the corporate. So in that case, loan number will determine branch name. If you know the loan number, then you should know that which loan the loan is issued by which branch. So then in that case, this table should be further decomposed. Okay, because you have a loan number. Let me consider this second situation. Let me just write use a whiteboard to explain that a little bit. Okay, so we have situation. So case one. Case one is each branch issues loans, issue loan numbers independently. Okay, so you can assuming that say for example Akron branch can issue a loan number 112, and Cleveland branch can also loan 112. So if that is the case, there will be no relationship. So basically, this table, this table have branch customer ID, and then loan number, and none of them depend on each other. Okay. So what kind of situation is this? This is more like a gerund multi-way relationship gerund. So basically you have something like this. Okay, so that ties customer and then branch and loan. And let's just say this is, and it's trying to make this clear. So this is just like this. Hold on. Okay, let me delete this. So it's going to be like that. And this is a gerund, okay? And so then you're going to duplicate the primary key from branch into here, customer ID into here, and the loan number into here. So this is a three-way relationship. Each one shows, each one ties a branch, ties the customer, and ties a loan, jointly. Okay. So this is case one. What about case two? Case two, assuming that each branch gets a unique loan number from the corporate. Okay, so if that's the case, then we'll have a situation that a branch customer ID or customer name, customer ID or just simply customer or loan number. Okay, so in that case, the loan number will determine branch. Does that make sense? So if you have a loan issued by Akron branch, and that loan has a unique number, and then that loan is issued by Akron, so you will be pointing to Akron. So we have a unique value, unique branch value for that particular loan. So if you know loan number, then you should know the branch. Does it make sense? Because each branch issues get a unique number from the corporate. All right, so if that's the case, then we have a situation that this also violates Boyce-Codd normal form because we have a determinant, but the determinant is not a key. Okay, what is so what is it? This actually determines so this loan number cannot determine customer ID because one loan may have multiple customers. So therefore, this table is not Boyce-Codd normal form. The table is not in Boyce-Codd normal form because due to loan number determines branch, but loan number is not a key, not a key for the table, for the entire table. Okay, and then how do we fix? We do the same thing as store normal form violations. So for that functional dependency, loan number determines a branch. We make a new table, and with loan number as a primary key, and a branch as a dependent column. And then everything else from the original table, which was just customer ID, everything else, right? Plus the transistor. So you need to get a transistor back. Loan number, make a new table. Okay? And then in this case, you have to use both columns as a primary key, right? Because one customer may have many loans, one loan may have multiple customers. So end the result, if you consider all the tables you have, then you're going to, this is more like a junction table, yeah, between customer and the loan, right? So you're going to have, let's look at the tables we already have. Okay, so we have one table. Let's just consider case 2. Okay, we don't consider case 1, let's consider case 2 only. So originally we have, originally we have this inside the PowerPoint. Okay, so originally we have loan number and amount, a new table, and this one was broken up into 3 tables, into 2 tables, right? So we have one table for loans and one table for, let me just minimize that. So consider these 2 tables we just obtained, plus one more table, which is loan number plus amount. So essentially, we end up with 3 tables from the original table on the second scenario. So what's the relationship between this? Now you have one table about the loan. Let's see, loan number. Let's see what's the relationship here. Okay, let's just see. Loan number and the branch, loan number and amount. So these 2 tables should be combined, you think, right? Because they're both determined by has primary key loan number, and so this table is actually is going to be relationship like this. You're going to have a loan number determines loan amount. It's just amount. Okay, just amount. And the branch. Okay. And then you have a second. So these two tables basically just like can be merged. Okay. Each loan has an amount and also have a branch, right? And then the second table just have customer and the loan number. Customer and the loan number. Okay, it's like a junction table. So what is missing is probably there is a table called customers somewhere, and that table has a many-to-many relationship with loans. Okay, let's do that. I'm trying to draw scrappy. Let's see. This is many-to-many relationship. So so this table, customer table, is missing from this picture, but essentially this by breaking up that original table into two tables actually, you're going to get this table and also junction table only. Customer table is missing. Customer. Small table. Okay. All right. So I think the customer table is missing in the picture, but just one table is given. From that, we applied Boyce-Codd normal form twice and get this result. Any questions? So that's why this table could have two different scenarios. One scenario is this, depending on how what's the relationship between low number and the branch, you may need to do it again. Okay. All right. Now let me see whether there's any other examples. The procedure to fix Boyce-Codd normal form is the same as the Thorne normal form. We already said that. And to fix Boyce-Codd normal form was violations is too much. Okay. And then the resulting subtables may be still be in violations. I just demonstrated that. Okay. Now let me give you a second example. This example is a little bit kind of a little bit it has some kind of a merit. You know what? Before this, let me show you. Do I have the example? Yeah, I have this example first. Okay, let's look at this example, and then we'll go back to the other example. Okay, so you understand this table is a violating second normal form, right? We did that. So basically, primary key consists of student ID and a course number, right? So now let's say whether this normal form violates Boyce-Codd normal form. Okay, so we do functional dependency. We say that student ID determines student name and the major. Is student ID key for the table? No. Course number determines title and the credit. Is the course number key for this table? No. It's only part of a primary key, right? So therefore, this second normal form violations, this table violates the second normal form and also violating Boyce-Codd normal form. Do you agree? Because if you draw functional dependency diagrams, say this one determines the name, but the student ID determinant is not a key for this table. So therefore, if your table violating second normal form, then it also violates Boyce-Codd normal form. Okay, so which one is stronger between second and Boyce-Codd? Boyce-Codd is stronger, right? So if a table violating second normal form, will definitely violate Boyce-Codd normal form. But if a table is in second normal form, but maybe still not in Boyce-Codd normal form. Okay. Now what about this table? This table violating Thorne normal form, right? So we have editor name determines the form. Does this table violating Boyce-Codd normal form? Yes, because the determinant editor name is not a key for this table. Editor name does not determine title, does not determine title ID. In contrast, on the contrary, title ID determines editor name. Title ID determines title. Title ID determines the form, right? But we have functional dependency where that is the editor name determines editor form. So therefore, this determinant. So we have functional dependency between editor name and the form, but the determinant is not a key. So the editor name is not a key for this table. So therefore, this table also violating Boyce-Codd normal form. Okay. So if a table violating Thorne normal form, it will also violating Boyce-Codd normal form. So between Thorne normal form and the Boyce-Codd normal form, which one is stronger? Boyce-Codd is stringent. It's more stringent. Make sense? Because if a table violating Thorne normal form, it would definitely violate Boyce-Codd normal form. Okay. But if a table is in Thorne normal form, it may be still violating Boyce-Codd normal form. I will use another example to demonstrate that. So therefore, this example shows that the Boyce-Codd normal form is stronger than second normal form, stronger than Thorne normal form. And as a matter of fact, the Boyce-Codd normal form is not fourth normal form, is not fifth normal form, is not a Thorne normal form. So then which normal form is it? So there's no, there's no numerical number to be attached. So if you do want to memorize this normal form to be stronger than second and third, you can just say this is like a 3.5 normal form. 3.5 normal form, stronger than second and the third, stronger than third. Third is stronger than second. right? So now let me go back to previous example. I think this, hold on. Previous example about to demonstrate that if a table is in Thorne normal form, but maybe still not in a Boyce-Codd normal form. So this is example, okay? So here we are assuming that each center, that's like the warehouse. There's the word the clubs like Sam's Club, Costco, those places. Okay, so let's say they have a table like this to manage their employees and their parts. Okay, so basically there are a few assumptions here. So each center has many employees, right? And each employee works for one center only, right? So Fairlawn Center or Cleveland Center. So maybe many centers, but then each center has many employees, but each employee works for one center. Make sense? Now each part can be stored in any centers, right? So all the centers, all the warehouses are selling the same kind of products, right? And each product have same part number, okay? And each center has many parts. That makes sense, right? Each part can be stored in any center, and each center has many parts. Okay, many items. You can think of the parts as items. Okay. Now each employee manages many parts, but each part is managed by only one employee. Each part is managed by one employee, and one center, of course. Okay. So, for example, if you have a particular problem with computer products, then you will find the employee who manages computers, and that employee is managing computers, okay, only, right? So, and you're not going to find a second employee who handle that, okay? So, assuming that each employee can manage many parts, many items, but each part is managed by only one employee. So, with that three assumptions, now let's look at this table. So, this table have the warehouse center, part number, employee number, and in stock and status. In stock and status. Okay, so if you're trying to do this as a third normal form violation or second normal form violation, you probably want to think of what is the primary key for this table. Let's try to do that. Okay, what is the primary key? Can you say it? What is the primary key for this table? Anybody? So which columns will determine every other columns? Functionally determine every other columns. If you know the center and if you know the part, will you be able to determine who is managing the part, the employee? You can determine employee, right? You can determine the in-stock status of the part, right? And also the status of the part. So essentially, if you have center and the part number as a primary key, then you will be able to determine every other columns. So therefore, center plus part number should make a primary key, should make a key for this table. Okay, that is candidate key. Does it make sense? So if you know the center, for example, you go to like Akron, Fairlawn, for example, Fairlawn warehouse, Fairlawn Sam's Club, right? So then you find that warehouse plus the particular part number, then you'll be able to see who is managing that, right? Because each part is managed by only one employee. Does it say that? Each part is managed by only one employee. So if you know the part, you should be able to determine who is the employee managing that. Okay, and then of course the stock, the in-stock status, how quantity, and whether the item is discontinued or not, right? So the status of the stock of item. So basically, center plus part number should determine that. So that should be a primary key, right? Now, if you look at non-key columns, or the non-key columns, do you say employee number determine in stock determine employee number, or status determine in stock determines status? Probably none of those. So therefore, this table is in third normal form. Do you agree? because the primary key consists of the center and the part number only. And then we just need to look at the non-key columns to see whether there's any functional dependencies among employee number, in stock columns, and the status. But you probably cannot find any functional dependencies among them. So therefore, this table is in thought normal form, right? However, this table is not in Boyce-Codd normal form. Why? Let's see, okay? So let's say why is not a function of the why is not Boyce-Codd normal form. Now, if I know employee, will I be able to determine the center? If I know the employee number, will I be able to determine the center? Yes, of course. Each center has many employees, but each employee works for one center, right? So if you know the employee, you know which center he or she is working for. So therefore, we have a functional dependency in that diagram. That is, employee number determines center. Okay. Now, given that functional dependency, then our next question to ask is employee number key for this table? Will employee number determine the part number? No, because each employee can manage many parts. Make sense? Employee number determines in stock status? No. So therefore, employee number is not a key, but employee number is not a key. Thus, the table is not in Boyce-Codd normal form. So that's the conclusion we made. And now let's say how can we fix that, okay? So we are going to use this functional dependency to make a new table, which will have employee number and the center, 2 columns only. Okay? And then everything else from the original table. Now remember, original table has center, part number, employee number, in stock status. So now center and the employee number should be removed because we consider only everything else. So everything else will be just part number, in stock, and the status. So everything else will be just a, what is this? Part number, in stock, and the status. Part number, in stock, quantity, and the status. Okay, so everything else. And then you need to add transistor back. So this employee number should add back to here. Employee number. As a foreign key here. Okay, so that's how we break up the original table into like 2 tables. So first table is about the employee and the center they work, and the second table is more about the item. Now, can you tell me what is primary key for this table? What should be a primary key for this table? Part number? Will part number uniquely determine in stock status? Will part number determines employee? Well, just remember that the part number is the same part number for different warehouses. So different warehouses may have different in-stock quantity and have different status. So therefore, part number cannot uniquely determine this functionally determine in-stock and the status. So you really need some other columns jointly determine. So the other column you probably need will be employee number. So you need both these to make a primary key for this table. Okay, and then after that, you check see whether there's any other functional dependencies that may also have indicating that there's violations of Boyce-Codd normal form. I do not see any. Do you see any? Employee number, in-stock status, employee number, and the part number. So remember, the part number is the same for every warehouses. Employee number, of course, if you know the employee number, then you know the warehouse the workforce. So then you'll be able to tell how much in stock and what is the status of that. Right. So these two these two should form the primary key for this table. Okay, so now this example demonstrates that you may have a situation like this. You may have a situation like in this table that it is in third normal form, does not violate the third normal form. We said that because the primary key should be center plus part number, right? And that primary key, and then everything else non-key columns. You do not see any non-key column depending on the other non-key columns. So therefore, this table is in third normal form. However, it's not in Boyce-Codd normal form. So now if we put down this like this, a table in third normal form may not be Boyce-Codd normal form. So may not, okay? A table is not in third normal form. We're definitely not in Boyce-Codd normal form. Okay, so from that too, can you make inference that Boyce-Codd normal form is more stringent than third normal form? So think of this way. So a table, if it's you say based on third normal form, you say that table does not have actual redundancy, right? Like this case, a table does not have actual redundancy. However, you use Boyce-Codd normal form, your result is different. You say no, the table still have actual redundancy, right? So the Boyce-Codd normal form is stronger. Make sense? So sometimes people use this 3.5 normal form to indicate that this is stronger normal form than the third one. Okay, what time is it? I think that finished the lecture we did not finish last time. I thought we have plenty of time to review, but I don't think we do. So let me close this to see whether you have any questions. Does anybody have questions so far? And we spent quite a amount of time to review your homework anyway. Okay, so that's review anyway. All right. Anybody has questions? If not, let's say the class time, we're supposed to finish by what time? By 9:15, right? So 5, let me double check. So sometimes I forget what time to end.
It's 9:15.
9:15. Okay, so we still have about 1 hour. Let's take a shorter break. Okay, let's take a break until 8:18. Okay, 8:18. Then we'll come back to answer your questions about your first exam. Okay, so let me stop recording. Pause, resume recording. Any questions about your first exam? Any concerns?
Professor Liu, is it the same format as the homework where we will submit the multiple choice questions and then we'll submit our other documents?
Yeah, it's the same format. You're going to have a multiple choice questions. So I just uploaded one sample exam that was done a couple of years back. That basically just give you idea of what the format should be. So usually I give you like a 70 or maybe 60% on multiple choice questions, and then 40 to 30% on hands-on questions. So hands-on questions, of course, this time will include data modeling, right? Build entity relationship diagrams, and then how to convert entity relationship diagram into a relational model, and then how to write SQL statements to implement relational model. Okay, and then if I give you a table, and then say that table may have violations of certain normal forms. So basically, we just did first, second, third, and the Boyce-Codd normal form. So these four normal forms will be on the exam. anything that like a fourth and a fifth, which is in the chapter but not covered, and we will not do that in the exam.
Do you want
Okay.
us to submit the actual files, or do we put the screenshots on a Word doc and submit as a Word doc?
I think just a Word doc should be okay for this exam.
Okay.
Word doc should be fine. No need to submit the entire project. Okay.
Will the time will be like 2 hours for the multiple choice and 1 hour for the main exam?
The multiple choice questions usually takes 30 to 45 minutes, no more than that. And then the rest time we'll be doing hands-on questions. So usually exam hour time is 2 hours. So we have like 2 hours 30 minutes, right? So basically we do not need a whole class to do that. Just part of a class, like 2 hours, 2 hours time. So what I would do is I can start maybe like a 10 to 15 minutes late, and then finish by 9 o'clock, something like that. So that way you have enough time. You have like a whole 2 hours to work on that. Now let me ask you a question. Do you have any problem to come to the campus next Wednesday to take an exam? Yes or no?
No, I don't.
You don't? What about Mariana? Do you have any problem with coming to campus to take an exam?
No, I shouldn't have any problems.
Should not have a problem. Okay, that's good. So next Wednesday, let's meet. You know the classroom, right? So yes, what is it? 160. Can somebody tell me what is the number? 162. CBA 162 is a newer computer lab. So if you go to CBA, there's a 101, 102. Those are two computer labs just outside, and then you go to the newer extension inside, and then you should be able to find the classroom. I think everybody else has been there, but Marina, you probably has never been there, the classroom. So just go to 162. I think that's 162, if I'm not wrong. Okay, so go there at what time? For 6:45, and then we will start the exam at like a 7 o'clock maybe, right? 7 o'clock, and finish by 9 o'clock. Any question? Okay. No questions about the format? Timing?
I have a question. How many hands-on questions do we have for the exam?
How many questions?
Hands-on questions, yeah.
How many questions in that sample exam? Let me see. So usually about the same number of questions. So I will give you definitely one question on entity relationship model. You will use data modeler to draw diagrams. Okay, and then you need to have a question on how to convert ER diagrams into relational model. Just for that, just make sure that I'm not going to use the same question for you to do both. Okay, like one of your homework questions, you do ERD first, and then you convert that ERD into relational model, and then you write SQL statements based on that relational model. So I'm not going to give you that. So that kind of question will be split into 3 questions. Okay, so I'll give you a question and then you draw ERD. And then I'll give you a separate ERD. I already draw the ERD, and then you create a relational model. Okay, and then I'll give you a relational model. So I give you a set of tables, and with a primary key, foreign key, maybe sometimes foreign key missing, you need to identify. But generally, I give you a set of tables, and then you create SQL statement to implement that relational model. You understand the point? The point is, I do not want you to make, for example, if you make a mistake in the first one, then you're going to make a mistake in the second one, third one again. So I want every part to be independent. Okay, so that way, if you make a mistake on ERD, it does not affect your performance on how to conversion of ERD into relational model or write SQL statements based on relational model. Okay, so basically those 3 definitely will be questions, and then you're going to have questions about normal forms. Okay, so I can imagine that it probably at least 4 questions, and then question can be big, small, so that really does not matter. So timing, in terms of timing, you definitely can finish in 90 minutes, but you have 2 hours to finish it. Okay, you definitely have enough time to finish your questions. So multiple choice questions usually 45 minutes. But if you're slow, you maybe take 45 minutes. But I have not seen any student do more than 45 minutes in the past. So it's basically the question has quite a few questions coming from your homework, past homework. So those questions you should not take much time to just get answers. But then there are questions that may be newer questions. There are some questions maybe just true or false, which are easy to decide. So it should average like 1 minute for 2 questions like that. So you should have no problem with timing. Okay.
Do we need to bring our laptops? Because it says the multiple choice is going to be online on your practice.
Multiple choices will be online. Yeah. So the computer lab have all the computers. So if you're used to your laptop, you can just bring your laptop. That's fine.
Okay.
Computer labs has all the computers we need to do the to do the exam.
Okay.
Okay. All right. Anybody else has questions?
Just one more. I just feel like, can you share one more example on the normalization, 1 and F2 and F? Yeah.
One more example of normalization. Okay. So you know what? Let's just do 1 question from your sample exam. How is that? You go to sample exam 1. Okay, let me share a screen with you. Let me see which screen I share, the second screen then. Okay, so let's do the sample example. That was 2016 question. Was released. Let me just share. Let's say, for example, this the word where I was talking about. So I give you a relational model here, right? So the table already. So just read the question here. The following table relation with PK underline and perform the following tasks. So you write SQL statements to create tables to make sure that each table has appropriate primary key and the foreign keys, right? So every table already have a primary key, foreign key columns, but maybe not all of them are identified, but you just need to identify. You do not need to duplicate anything because they are already in there, okay? all foreign keys or primary keys are already duplicated, so you do not need to create new duplicates. Okay, so we have a table called courses, the course number, sections, has a course number, has a course section, and then so definitely there's like a weak entity, right? There's a course number, so that's the same thing, right? So that's duplicate, that's foreign key, so there's more like a weak entity. There's a section number in here. And then you have a prerequisite, so prerequisite have a course and a prerequisite, and also have passing score. So this is more like a associative entity for the many-to-many relationship between courses, right? So you already have two foreign keys. That's the course, that's course number. Prerequisite, also course number, right? So make sure you know how to identify the structure of the table. So even though in this case I told you that the primary keys identified, sometimes it may give you tables that not all primary keys identified. Some of them may be identified, but then you need to identify foreign keys based on the structure, based on your understanding of the relation model. Okay, and then based on that, you just need to write SQL statement to implement that. Does it make sense? So you do not need to, for example, you think this course number should be also in the prerequisite, so duplicate this course number again into here. That is not what you're supposed to do. Okay, so because this is already relational model, it's not just it's not ER diagrams. Okay. All right. So now this is a normal form problem here. Let me just say here. Okay. So that table, company use this table to manage the ongoing project assignment using the following database table. Does it conform to the second normal form? Why or why not? Does it conform? If it's not in second normal form, normalize it so. Okay. So usually let me give you a clue. Okay. So if I say is question like this is probably not just, it's not yes, it's probably no. Okay. Because if you say yes, then really there's not much to do. Okay. So we need to use second normal form criteria to make a judgment to see whether this table has actual redundancy or not. So what we need to do is, first of all, let's say what is the primary key for the table? What is the primary key? So the project is about a project, and it's about an employee. Okay, and then their participation in the project. So this definitely you have a relationship. Let's say based on common sense, one employee may participate in many projects. Is that true? Let's check. Okay, so one employee ID. That's 9088. Yeah, it appears twice. So that means one employee may be in several different projects. Okay, second, one project may have multiple employees. Is that true? Let's check. Okay, so this is HD234, HD234. Yes, this project has 2 employees inside. Okay, so therefore, the relationship between project employee should be many to many, right? So therefore, this table should have a primary key consist of both project ID and also employee ID as the primary key. Does it make sense? That's what I was just trying to use, the knowledge of cardinality to make a judgment about whether something should be considered as one-to-many or many-to-many, and then based on that, we decide the primary keys. Okay. So if you use a project ID alone, it cannot be primary key. Employee ID alone cannot be primary key. Can you tell? Because the project ID is duplicating in this column. Employee ID is also duplicating. So none of these 2 columns can be primary key alone. Okay, can be primary key alone. So you have to use both as a primary key. So after that, so you decide this primary key consists of 2 columns. Right, so we can just highlight these 2, okay? Highlight this one as a primary key. Now let's draw functional dependencies. Definitely, description depends on the project ID, description. And the employee name depends on the employee ID only. What about title? What about title? The title depends on employee ID alone. So for that, we can check. So for example, this employee 9088 has director here, and then 9088 has architect here. So therefore, the title title does not depend on employee ID alone. Title should depend on also project. So this title depends on both. What about the work hours? Again, we can check. So does different employee have different work hours? Has same employee have different work hours? Let's check. Okay, 9088, 5 hours here. 9088 have 20 hours here. So therefore this also depends on both. Okay. So therefore, if you draw functional dependencies, will look like this. So let me put this up here. So you're going to have, let me put this up. Okay, so you're going to have a project. So let me draw the functional dependency diagram. So project, okay, description, employee ID, employee, title, and work hours. Okay, so project depends on the determines description. Employee ID determines employee name, but title and work hours depend on both. Okay, so this is second step. After we have this functional dependency diagram, now we can make a judgment to see whether this table has second normal form violations. So essentially whether it has partial functional dependency. Yes, we do, right? We do functional partial. This project is a part of primary key, student ID, employee ID is a part of primary key, but they do determine some other colors. So the table is not in second normal form because of partial functional dependency partial functional dependencies, just FD. Okay, so which are project determines description, and then employee ID determines employee. So those are two partial functional dependencies. So because of that, we need a fix. So to do that, we are going to split that into split the entire primary key into every part. And then together, project, employee ID. So employee, this determines description, and this determines employee. And this determines both. So that would be title and work hours. So you end up with 3 tables. So you know what 3 tables, right? So this table, this one make a new table, this make a new table, this make a new table. So the last table is essentially like a gerund between employee and the project. Okay, make sense? Now let's continue. Let's see whether I have any questions about. Oh, okay. There's one more normal form here. Okay, let's look at here. Let's see whether there's any. Oh, this is a Boyce-Codd normal form. Okay, so the following table is for Ohio Polytechnic. That's University of Akron, right? Assuming the school has multiple campuses and offers the same set of courses on each campus. Okay. Each campus designates a specific department to manage each course. So each course, so what does it mean? Each course, each specific department manages each course. Okay, so that means if you know the course, then you should be able to identify the department. Okay, just read some kind of keywords like that. Okay, to use human resource management, the school makes all department names unique on all campuses. So department names are unique on all campuses. Does that make sense? Okay, so what does that mean? So it means if you know the department, then you should be able to identify campus, I believe, right? If you know the department, you should know the campus, because all department names are unique. So even though there's a management department, but that name may be only for agro, and management, some similar department in Cleveland might be using different name. Okay, so I believe this is what it means. To use human resource management, the school makes all department names unique on all campuses. No two campuses have department names identical. That's right. Okay. Does this table conform to Boyce-Codd normal form? Yes or no? Let me see. Okay. So here we have campus, department, and course number, and the student count. So basically, the student count really depends on the course and also campus history. And then, so for Boyce-Codd normal form, we do not need to know what is the primary key. So we just need to know all possible functional dependencies. Okay, so what functional dependency we can think of here? Okay, so I think we said the department. The department should identify campus, right? Is that one? So if you know the department, you should know what campus is it. Will department be the key for the table? Well, department may have multiple courses, so department cannot uniquely determine course number and also cannot determine a student count. So therefore, this department determinant is not a key. Does everybody follow me? Does it make sense? So each campus designated one specific department to manage each course. Specific department, so that means that on the particular campus, if you know the department, if you know the course number, then you can identify the department. So if you know, so the primary key, I think for that table, if you need to identify primary key, should be campus and the course number, I believe. If you know the course number and the department and the campus, then you know the department and you know the student count, right? You know student count. Okay, but the course number alone cannot be a key, because so maybe this is for Akron and this is for Cleveland. So even though they have same course numbers, but they have different number of students on different campuses. Okay, so only thing we are sure that in this case we have a situation that if you know the department name, then we can determine campus. However, but department is not a key for the table. Department cannot be key, right? Department cannot determine. Department can determine campus, but department cannot determine course number and the student count. Okay, that's the reason. Now with this, now we say this table is not in Boyce-Codd normal form. Okay. Okay. Thus, the table is not in Boyce-Codd normal form. So to fix it, so we're going to follow the procedure. So we use department, determines the campus to make a new table with department as a key and the campus as a non-key column. And then everything else from the original table. So our everything else basically in this case is course number and student count. There's two columns. Okay. So everything else, so course number and the student count. There's two columns, plus this original transistor, this transistor back in here. So make that as part of primary key. Okay. No, we make that as a foreign key, but then let's say, I think in this case, we do need to use this as part of primary key. So this is going to be a foreign key and also going to be part of primary key along with course number. So if you have course number and the department together, then you should be able to identify the student count. Okay. And then this table is already Boyce-Codd normal form. Okay, because the only determinant is this one. Department determines the campuses, but the department is already key. Now, do we have any other functional dependencies in here? So we do need to have department, course number, and the department together to jointly determine student count, but that is determinant. That determinant is already key. So therefore, this table is already Boyce-Codd normal form. So the fixing procedure for Boyce-Codd normal form is not clean as in Thor normal form. So you may need to check that again. Okay. So therefore, this is the result. So you break up that table into two tables. One table shows department names and their campuses, and then second table shows student count for each course inside each department. Okay. So therefore, this is a Boyce-Codd question. Do you have any questions about this one? Convert that into a relational model by Arc implementation and then write SQL statement to create tables or coordinate. So you are going to create one table for corporate. The table does not have an ID, so you need to create artificial key for that. You want me to do that, or you think you're okay? Do you want me to do that in whiteboard?
Yeah,
Yes,
you can do it.
Yes, I can do it. Or let me just do it. So let's do that. Let me put this up. Oh. Let's put a whiteboard in here. Okay. So you're going to create table for subtype first. So that would be corporations. So corporations have existing name and existing text ID. That's optional. And then the table does not have ID, so we need to make up ID. So maybe this is a corp ID as a key, as artificial primary key. And then we are going to create a table for what is called? Rule, I think it's called proprietor, I think. It's missing missing the letter. So proprietor. So for that, you do have ID, that is social security number, that is going to be primary key here. And then you have a last name. So for that table, you do not need to have extra artificial key. Okay. And then we can do the supertype. So supertype of businesses, which will have the following table, following columns. It has ID column, so that will turn to primary key. You do not need to create artificial one. And it has a phone, optional, and the fax, not required, not mandatory. And then we do need to duplicate the primary key from the subtypes into here, okay? So we are going to have corp ID as one foreign key, and that foreign key is always optional. And then we have SSN as another foreign key. That foreign key also is not mandatory. So duplicate the primary key from each subtype into supertype, like that. Okay, so we handle that big box, small boxes. Now we have to handle two more boxes. And the first one is servers. the servers have host, which is ID. Let's just make that as a key. Okay, there's a key here. So let me just try to make it I'm trying to erase this. Okay. Okay, host, which is ID, and that's the primary key, and then we have IP address, IP, which is required. That's one table. And then we do the second table, which is a weak entity, so it's credit cards. So credit cards. Okay, so credit cards has a couple columns. So credit card number. It's just the space is not big enough. Let me try to reduce that. So what is this? Why I don't see that? Okay, let's just delete this first. Okay, so let's do it again. So let's say this is card number, primary key. And then along with some other information about the credit card, that's credit card. And then type, and then expiration. So credit, and then type, and expiration. So let's move to a little bit right. Expiration, expiration date, I think. Okay. All right. So we have one table for each box. Now let's say we are going to handle relationships. So the weak entities must be handled first. Okay. Weak entities must be handled first. So here we have one-to-many from businesses to credit card. Hold on, is this connecting to this one? Yeah, so it's not very, so this line is actually crossing. So basically this credit card is only for those proprietors. So we have the duplicated primary key from proprietors into here. So that would be social security number. So you need to put social security numbers as a foreign key and also as a part of a primary key, because that's a weak entity, right? Does it really say that? It's because there's a weak entity. So duplicate the primary key from one side, which is a priorities table, into credit card. And also because this little bar, you need to make that the primary key as a part of primary key for a credit card. So credit card number is basically going to be part of a primary key. So credit cards going to have two columns as a primary key. And then we have another relationship, which is a many-to-many relationship between, so in this case, it's between business and the servers, right? So you're going to create a junction table for that. So junction table, let's do that here. So first of all, for business, you have ID, which is a primary key here. So we can just use ID, or we can just say this is a business. So this is primary key coming from ID, and that's going to be required, and it's going to be part of a primary key because that's how we do junction table. And then the second part is coming from server. So server has primary key as host as a primary key, as host. Okay, so we can have host as a foreign key here, and it's required, and also as a part of a primary key. So therefore, this is a junction table. Okay. Now, so that's it, right? So now you just need to create SQL statement. Do you have any problems with that? SQL statements. I think it should be okay, right? So only thing you need to do is just make sure that you have to use arc implementation. So either this is not or this is not. Okay. So write SQL statement to implement that only one of these two can have values. Does anybody have a problem with that?
So Professor, in credit card table, SSN will be required foreign key, right? Which will be also part of primary key.
Yeah, because as a part of primary key will be definitely required. Yes.
Okay. Yeah.
Yeah. That's right. Okay. Any do you think you have any problems writing SQL statements for this kind of tables? If not, let's just move on. Say we have one more question here. Let's see. So this question is ask you to draw entity relationship diagram, I think. Yeah, develop an ER diagram using data modeler. Okay. So here, General Clinic has recently decided to develop a new database for their customers. So identify the customer is one object, as well as the staff members to make appointments. So appointment is one, okay, and for doctors to order tests such as X-ray, blood count, so on and so forth. So based on that one sentence, you can identify how many objects. You identify customer object, right? Staff members, okay, and appointments, doctors. So now you can see that you may need to use like supertype, subtype. So maybe like general employees have a subcategory as doctors and staff members. Okay, and then auto test. So now you know how to handle test, right? So test, you can be confusing names. You can have a test, catalog test, and actual test that is ordered as scheduled. Okay, so if you're trying to put everything on this diagram, then you probably see you're going to have a customer. Okay, appointment. Then you're going to have employee, and that will have two subtypes, maybe like a staff and physicians, something like that, right? So they may have different attributes. Okay. And then you have test, catalog test, and you may have actual scheduled test. Okay, so this relationship should be always like a weak entity here. Okay, and then you're going to have orders. The physicians make these orders, and orders is order test, right? One order has one test, I believe. Okay. And after each visit, one or more follow-up visits may be scheduled for succeeding treatments. So now we have treatments and visit. So what is this trying to differentiate that? So visit, you can consider visit as same as treatments. Or you could consider a visit is different from treatment. Treatment is more like a detailed procedures be performed. So if that's the case, then you are going to create two separate things. So you're going to have visit, and then you can create procedures. So let's just say procedure is same as treatment, okay? And then there's a follow-up procedures. So follow-up procedure, follow-up. So then you're going to have some kind of a recursive relationship here. Okay, is that one-to-one? I think it's just one-to-one, because each visit is going to just have one follow-up visit. So let's just do just one here. Okay, but it's always optional to optional because it is recursive. So that's what follow-up is handled. Okay. And then each visit is going to have perform multiple procedures. So this relationship should be each visit has performed multiple procedures, and each procedure may be used in multiple visits. So there'll be many-to-many relationship inside. Okay. What else? Track follow. The clinic realized that the most difficult part is how to record test results, which include images, numbers, texts, and text. And tests may be performed by lab across the nation and read by licensed professionals. Then actual result and the readings will be sent to the clinic for the primary doctors to make a diagnosis and order prescriptions. So the last part is how we handle different kind of test results, where do we put test results. So we have actual test here, scheduled test. Then this scheduled test, each test is going to have multiple different results. So we can just put results, test result in here. Okay, test result. So that should be handled as a weak entity and depends on the scheduled test. And then, so you have test results. So each test may have multiple test results. And for that test results, so it says most difficult part is how to record test results, and which include images, numbers, and text. Okay, and so how do we handle that? Is of course there are a couple of choices here. You could make different test results as different attributes. But generally, for each test result, you may have like a test result ID, right? And then result, obtained date, time, right? So general attributes. And then you may have a separate like subtypes. So maybe there's one for just say images, image, okay? And then you may have some other test results just as a subtype in there, inside, okay? And then the test results, so that's how we handle that. And then the test will be performed by labs. So we are going to have test attached to labs. So here we are going to say for this, for example, each test is performed in some kind of lab, but one lab may have many of these tests scheduled, right? So it's the one-to-many relationship. Okay, so there's another object identified. And read each test results may be read by professionals, and actual results will be sent to the clinic for the primary doctors to make decisions. So then the question, the test results may be read by professionals. So we may just indicate. So here, each test result may have a reader. So then we can just have attribute, indicate as reader. Or we may just create a separate entity called readers. Okay, and then each result will be read by one reader, and the one reader may have multiple of these results. So let me just try to make it clear here. So that should be general case that one reader may have multiple test results read. So here we have information about those professionals who read the test results. So generally, that should be just like a skeleton of this ER diagrams. So this question is pretty open, right? It does involve quite a few objects. So so this type of questions we usually be putting the last because that really depends on how much time you have, and this could take a little bit of time. Unlike the previous questions, those previous questions should be just like easy questions, and then they basically just guarantee that you have you'll get a certain number of points easily. But the last question is usually pretty open. Okay, so it depends on how much domain knowledge, how much you know about the clinic, about the test, about physicians. Then the ER diagram can have a different level of accuracy. Okay. All right, and let me say whether I think basically did we go over every questions? Yeah, that's all the questions. Okay. So
Professor,
yeah.
how would you like us to submit the relational models? Are they handwritten and then scanned in?
You can, yeah. You can handwritten, and then you can just give me the paper because we're going to do in class, right? So you're going to just give me the paper you draw.
Okay.
Yeah.
Got it.
Yeah. All right. Any other questions? Let me stop sharing. Okay. And then stop recording.